Yeah.
Okay, great. Yeah, so hi everyone. In this talk, I'll be presenting our work which studies behavior of metagradients in non-stationary environments. So let's start by discussing why is this an interesting question. So agents which learn in continual non-stationary setting, they need to be capable of learning throughout their entire lifetime and in very different settings, which may require adaptation of update rules. So for example, consider an environment in which the reward and transition function of the underlying MDP changes at regular intervals. So after each change, and depending on task difficulty, the optimal strength of regularization and learning rate may need to increase. However, we may not know in advance how these update rules should be updated, and so automatic adaptation of update rules is very desirable in such environments. So what we do in this work is we aim to improve our understanding of adaptive optimizers in such environments, and we are going to focus on white box metagradients as they have shown the greatest empirical gains in reinforcement learning so far. So quick recap. So what are white box metagradients? So those are the methods which tune only a select subset of hyperparameters of the update rule. For example, discounts of policy corrections or regularization weights, and they tune them by using gradient-based methods. So what does this mean more specifically? So in general, in metagradients methods, we are going to differentiate parameters such as weights of the policy and value function, and the metaparameters, which are these tunable subset of hyperparameters. The parameters in this setting, which are in this slide colored in blue, they are trained to minimize the inner loss, whereas the metaparameters, which in this slide are colored in red, are trained to minimize the outer loss. The parameters depend on the metaparameters through the gradient-based update rule, such as gradient descent. So since the outer loss typically depends on the metaparameters only through their influence on the parameter values, computing gradients of the outer loss with respect to metaparameters involves only backpropagating through the history of parameter updates. And we are going to refer to these gradients as metagradients. So one thing to note here is that since the white box metagradients are completely memoryless and they can only kind of track what good metaparameter values are, they lack the ability to learn from experience. So to address this particular problem, in recently proposed variants of these methods, the metaparameters in the update rules are replaced by learn metaparameter functions of the selected context features. And here I'm coloring the context features in green. We are referring in this paper to these approaches as contextual metagradients. So what are context features here? So they can be any kind of learning or environment statistics that capture information that is relevant for adaptation of optimizers. Some of the good candidates for context features are histories of rewards, TD errors, and task beliefs. And by making metaparameter functions of contexts, now optimizers can learn from experience. For example, such optimizers can learn to quickly increase the learning rate or the rate of exploration when the context features indicate a drop in agent performance. And again, if you missed it, like the important thing here is that instead of learning just the metaparameter value, now we're going to learn the parameter values of this parameters of this metaparameter function. It's a little bit confusing, but if it's still confusing after this talk, please approach me with questions. So with this in mind, we are going to propose the following research questions. So first, we are interested in whether metagradients will indeed benefit from this contextual information. And second, what kind of functions of context will be learned in this process. Then we also are going to examine how important is the choice of contextual information in this case. And lastly, how does the performance of metagradients, with or without context, depend on the rate of environment non-stationarity? So to answer all these questions, we are going to run the experiments with the following setup. So we will use either actor-critic agents where we tune entropy loss coefficient, or we're going to use k-lambda agents where we tune the epsilon of the epsilon greedy exploration. So we're focusing on exploration metaparameters. As an outer loss, we will use either kind of standard metagradients loss or the bootstrap metagradients loss. And as context features, we will compare kinds of simple context features, which consist of the history of rewards, and we refer to these as just reward. And we're going to compare them to a richer set of features, context features, which consists of the history of rewards, TD errors, and values. And we refer to those as rich in the paper and in this presentation. And in terms of environments, so we run the experiments on these two simple non-stationary environments. So the first one, which I'm calling here two colors. Here, the agent is in green, and it's tasked with navigating to either red or blue square. Which of the two squares carries positive or negative reward changes every 100,000 steps. In the second environment, both reward and transition function change every 100,000 steps. The reward and transition functions in this case are randomly generated, and we study the two different variants of this environment. So in the first variant, there's a total of 4 different possible MDPs, which means that the same MDP will be experienced multiple times during a measured lifetime. And in another version of this environment, we'll be using a total of 1,000 different MDPs, which means that it's highly unlikely that the same MDP would be experienced more than once during a measured lifetime. Okay, so on to the experiments. So first, we're going to compare the lifetime performance. So by lifetime performance, I mean, what is the total reward after 10 million environment steps? So we'll be comparing the performance of baseline agent and the metagradients methods with and without context. So first, we're going to start with the two MDPs environment. So on the left, you see the results with the actor-critic agent, and on the right, you see the results with the Q lambda agent. The first row in both tables is the baseline agent. So the baseline agent does not tune the metaparameters. The second and third row are metagradients with different outer losses, while different columns correspond to either no use of context, reward context, or rich context. What we find is that across different agents, outer objectives, and contexts, the use of context is indeed helpful and often necessary for improving the lifetime performance of metagradients. So we run a similar thing on the multiple MDPs environment. In this case, different rows correspond to a baseline agent, metagradients with no context, a reward context, or rich context, while different columns correspond to those two environment settings, so either 4 or 1,000 MDPs. So we see a similar result here, and we also find that there's much greater improvement seen when the number of MDPs during a lifetime is greater. So in a way, like the environment is like even more non-stationary. So next, we're going to examine what are the learned metaparameter schedules and functions in this setting. So first, we're going to look at the metaparameter schedules without the use of context here on the left, and with the use of reward context on the right. So what we're plotting here is learned entropy loss coefficient. So that is the orange curve, and the mean reward during training, so which is blue curve. So you can see that there are like these drops in performance at regular intervals as measured by mean reward. These correspond to task switches. So every single time you switch a task, there's a drop in performance, which is then followed by recovery. So we find it like when you don't use the context switches on the left, the metaparameters just do not change quickly enough to facilitate faster learning when a task switches. Whereas like when you do use context, there is this like very quick adaptation increase in the value of the metaparameter that follows like the task switch, which is what we actually want. Next, we're going to look at the learned metaparameter functions when using contextual metagradients. And in all of these cases, in this case, the context is again just reward features. And we're going to look at how are these learned functions changing during training, during the lifetime of the agent. So the way we're going to do this is by tracking outputs of metaparameter functions for 5 qualitatively very different context inputs. So the way we chose these inputs is kind of to represent different learning situations. So for example, is the performance of the agent increasing, decreasing? Is the reward of the agent is getting very low? Is it very high? And yeah, so what we find here is that, another important thing here is that the metaparameter functions are not trained on these inputs. They're trained as before. So the only thing we do here is we just input these particular context inputs, these representative context inputs, and we're logging how are the predictions for those inputs changing during training. So yeah, here are the results for 2 MDPs environment. And you can see, so like it starts with kind of same prediction for all these context features because it's not differentiating them, but over time it's learning to predict very different metaparameter values for different context inputs. And we are finding that these context predictions are actually quite meaningful. It's what makes sense. So for example, predicting higher entropy when the observed rewards are very low. And we also find that these learn mappings converge over lifetime, which is also another desirable feature. We find a similar result on multiple MDPs environment, with the main difference in this case being the higher variance in predicted metaparameter functions, which is kind of to be expected, given that MDPs are the rewards and functions of MDPs are randomly generated. Okay, and then next question is, so which might be on your mind as well, which is like, okay, so how did you choose these context features, and how important is the choice of context features? So that is a question we're going to examine in this set of experiments. So one concern you might have is, well, if you make the context too rich, there's a risk that you might start overfitting to particular contexts. And so what we're doing in this experiment is, so we have a sequence of experiments. So we start with comparing just metagradients with, using metagradients with no contextual information. And then we slowly add one. So in sequence of experiments, we add one by one different kind of context feature. So we start by adding just like the value context features, then we have value reward, then value reward TDR, et cetera, all the way until you add like the entire state distribution as a contextual features, as contextual feature. On the left, we tune only entropy loss coefficient, and on right, we tune both entropy loss and L2 regularization coefficient. So what we find here is that adding most types of contextual information is almost always better than not using any contextual information. And in general, richer contexts lead to better performance, with the exception being state, which is highly dimensional and doesn't carry much information about what good metaparameter value should be. And lastly, we examine if metagradients become more important as the rate of non-stationarity increases. We expected that metagradients would become more important in more non-stationary environments. The way we control the rate of non-stationarity is by changing the period with which the underlying MDP changes. So if we if we switch the MDP more often, then we're going to say that environment is like more non-stationary. So on the left, there are the results on 2 colors environment, and on the right, there are results on multiple MDPs environment. So, so contrary to our expectation, we found that like it's not always the case that metagradients perform better in highly non-stationary environment. There is some kind of a sweet spot where they do better reliably. But in general, if the environment is very, very highly non-stationary, metagradients are not necessarily going to do better. However, we find that if we do use contextual information, then the performance boost we see with metagradients is going to be greater. And on right, at least in one of the environments, even in highly non-stationary environments, the performance is like really, really high. So we don't see this trend of like metagradients performance necessarily kind of dropping if the rate of non-stationarity increases. In fact, it kind of improves even more. So yeah, thank you for listening. Unfortunately, I'm not there with you, but if you have any questions, you're very welcome to message me in my email or ask me now.
Any questions?
Hey, Jelena, great comment. I have a really dumb question to ask you because I think I missed it early on. What is the inner metaparameter that's being optimized in this case?
So
like,
what is being
learned by metagradient descent? Like, what is the inner thing that's being optimized that we're checking to see how robust we are across non-stationary environments?
What is the thing that's being optimized?
Sorry.
Yeah, like the parameter that's being optimized. Sorry, very dumb question.
Yeah, so the question is, what are the metaparameters that are optimized, in case you...
Sorry. Okay. Yeah, sorry, I may have gone over that too quickly. So there are two. So if we use actor-critic agent, then we're optimizing the entropy loss coefficient. So that's basically how strongly are you regularizing towards how the entropy regularization, how strong is it? Yeah. And then if you use Q lambda agent, then it's going to be epsilon of the epsilon gradient exploration.
Yeah, that makes a lot of sense. Very cool. And do you mind going a few slides forward if you don't mind? Okay, cool.
I'm gonna ask Razan for translation again because like the sound does not carry quite right to me here.
Yeah. Do you mind going like
Sorry.
Or you don't have control.
Is this better?
Okay,
Okay.
this is much better. Thanks.
Awesome. Do you mind going forward a few slides?
Yeah.
The one where you present, I think it was the one back there. Or one ahead, I think.
Here?
Yeah,
Here?
that's the one. The
Okay,
one where you
okay,
presented the initial results. Actually, the one just previous. Sorry, there's a lag.
Oh, okay. Okay.
Yeah. So it seemed like there was a little bit of overlap almost between the two methods when you compared the standard deviation or the standard error. And like, I mean, it's really cool because that's consistent from, you know, non-stationary and underlying learning methods like ordinary Q learning or something like that. When we add sort of like non-stationary learning methods. And I'm wondering if you have any ideas for how we could improve metagradient processes to sort of expand the gap between the meta-learning processes and that are adapted for non-stationary methods and just sort of like the base metagradient methods that we have today. Like more of a future work question, if you know what I mean.
Oh, future work for these kinds of stuff. Yeah. So there's like a lot of things we haven't tried, obviously. So is your question about like contextual metagradients or metagradients in general?
I mean, both, because like contextual metagradients are a way of trying to like adapt more robustly to the non-stationary problems. But like, I mean, that even in underlying like non-meta learning processes, we often have difficulty beating like stochastic gradient descent. Stochastic gradient descent with a good, well-tuned step size is very powerful and hard to beat. So like, you know what I mean? Just along those lines.
Yeah, I could tell like maybe about like some of the problems that I encountered working with metagradients, and then and some of the problems that I've seen with contextual metagradients as well that I would love people exploring more. I hope, would that answer your question?
Yeah, sure. No, yeah.
Very
interesting work. Thank you for sharing.
Yeah, no, thank you for great questions. So one thing I noticed is like, it seems like with metagradients, there is, for example, the reason why, so you would say like in this slide here, so it seems like metagradient, so metaparameter isn't adapting at all unless you use context, which is kind of odd. So you would be like, okay, well, maybe if I just increase the meta learning rate, then I would be able to adapt it like fast enough so that it actually does, so that like metaparameters does increase fast enough. But this doesn't seem to be happening. So if I increase the meta learning rate, then just the metagradients become too unstable. So I haven't seen like this problem of like instability of metagradients being explored a lot. I think that'd be an interesting thing to look into. Oh, I think we're over time. Okay, please like email me and I'm welcome to talk to you more about this.
Cool. Thanks a lot, Jelena. Let's give her another round of applause.